What does it actually mean to have an efficient feature representation? Let's look at this using a simple toy example. Let's go back to our imaginary world of only 3 by 3 images and reduce this world even further. Let's say that we use images to communicate, and we only have 7 possible images that we use for communication, and they look like this. Each of these images has only one of 3 values in it: white, gray, and black. And let's say the intensity of the black color is equivalent to the intensity of 2 grays. This means the black color can be achieved by adding 2 grays together. Our goal is to find an efficient feature set that we can use to construct all 7 images. Think of a feature set like the building blocks that we want for representing our data. It's like the basic Lego pieces that you need in order to build all the objects that you want. Looking for an efficient feature set is equivalent to figuring out what types of Lego pieces should we have in our set so that there are a minimum different types of pieces, and yet we can still build all the objects that we wanted. We're looking for the most powerfully expressive set of basic Lego pieces, such that the fewest variety of pieces can still construct all the objects that we need. Going back to our visual images example, instead of Lego objects, we have images. And what we want is to be able to find the smallest basic set of image patterns from which we can construct all 7 images. A default feature set might be to use a single pixel representation. So here, each feature is an image that has a single gray square, and there is a feature corresponding to each of the 9 positions for our 3 by 3 images. This is a feature set of 9 features. Using this basic feature set, each of the 7 images in our world could be constructed as follows. The first image would be constructed using 1 times each of the 4 corner features plus 2 of the features with the center gray square. Remember, 2 grays equals a black. Similarly, the second image would be represented as 1 of each of the features that represents a single gray square in a non-corner side position, plus 2 times the feature with a center gray square. And the rest of the 5 images can also be represented with the individual pixels in this way as shown. This is a very simple feature set with 9 features that we can use to represent our world. However, it's not as efficient as we could be. We only have 7 images to represent, and we could have fewer features if we just used each feature to be one of the 7 images itself. We're better off in terms of efficiency if we use a basic feature set that consists of just each of these 7 images. And now we have a basic set of 7 features, 1 feature for each image. And this is more efficient than having the 9 pixel-based features. However, we can still be even more efficient. Here is shown a feature set of 5 images. We can construct all of the 7 images in our world from these 5 basic images. How each of the 7 images can be constructed from the 5 basic images is shown on this slide and the next one. So we've found a feature set of 5 basic images that can represent our world of 7 images. And this is more efficient than using the 9 pixel-based feature set, and also more efficient than using the 7 images themselves as a feature set. Having an efficient feature set allows us to represent the world that's relevant to us with fewer basic components. And this efficient feature representation is the type that we need in order to recognize objects in a world of images where the possibilities is a number with greater than 1,000,000 zeros. We want a representation that specializes in representing images that are relevant to us. Using efficient specialized representations also means that we can measure differences in terms of the features that matter to us. If we had used a pure pixel by pixel representation, 2 images of faces could differ from each other on a pixel by pixel basis as much as a picture of a face versus a white noise image. But if we were to use an efficient feature set that detected the characteristics that most distinguish different faces and that are most representative of faces, then it is clear that the difference between two faces is much smaller than the difference between a face and a white noise image. Our visual neurons are especially adapted to recognizing the features that are most useful for distinguishing objects that are relevant to us in the world. This is also what deep neural networks do. Deep neural networks learn efficient feature representations that are specialized to detect what is relevant for the information processing problem. This is why we're able to recognize objects, even if the number of possible images is a number with at least millions of zeros behind it. I want to say one more thing about biological neural networks versus artificial neural networks. Researchers who developed artificial neural networks were inspired by what we knew about the function of the biological neural networks in our brains. However, I'd like to emphasize that despite taking some inspiration and having some analogies, artificial neural networks do computations in an entirely different way than our brain's neural networks. But there are some analogies, and one of them is feature representation that's efficient. Both deep learning neural networks and our biological neural networks use a similar strategy in that it uses feature sets that are the most relevant for the information processing task at hand. Now we've gone over how we might represent a variety of different types of data to our deep learning model. We also discussed the importance of feature representation and why it's so powerful that deep learning models are able to find an efficient feature representation when we're dealing with complex information processing problems. The other thing we need to do is to decide what kind of training data we need for our model, and this relates to the type of learning problem that our model will be solving. In the next lecture, I'll be going over the three main types of learning problems that machine learning and deep learning models solve.